The curation facility at NASA's Johnson Space Center is now more than 50 years old. It started out as a place for geologists to train some of the astronauts into acting like geologists on the moon, but then served as the first curation center for NASA return samples, and it's maintained that ever since. So over 5 decades, we've begun curating more than just samples from the moon. Let's start with that. So there are almost 400 kilograms of material collected by the Apollo astronauts, uh, stored very safely and carefully in a hurricane, termite-proof facility in Houston, if that's possible. And these samples some are still being exposed for the first time now. There's a lunar core that's being opened as I speak. And there's still one or two more left that haven't been opened. So even after 50 years, there are still lunar samples which have not really been fully characterized yet, amazingly. And of course, techniques have developed over 50 years to where we can do a lot more with these carefully maintained samples than we could in 1969. And that's the reason for keeping them in a safe, curation, contamination-proof housing. We also have about 10 grams of material collected by the Soviet Luna missions. There was a sample trade back in the 70s, I think the 80s too, to dealing with those samples. So there are samples from all spots collected by humans on the moon. And those are maintained, and you can ask for those now. And many of the scientists say lunar samples weren't even born when these samples first came back in 1969. So the next set of samples created at Johnson Space Center were meteorites collected in Antarctica. Those were first spotted by Japanese scientists in 1969, the same year as the Apollo 11 mission. And over the years, there have been tens of expeditions to Antarctica from the US, as well as from Japan, Europe, Soviet Union, other countries, including now China and Korea. And at JSC, we have more than 22,000 meteorites collected from Antarctica, which have sampled dozens of asteroids at least, also the moon and Mars, and probably the large asteroid Vesta. And here you see a collage of pictures down in the lower left. There's a lab. It's one of the rooms in the curation lab. And you see on the upper right the collection of the largest single stone found in Antarctica, which is now sitting in its own little housing facility at JSC. And those meteorites have every year new meteorite types turn up, and we're always hoping to get something from, say, Venus or Mercury, perhaps. But in fact, the first meteorites recognized from the moon and Mars were verified from samples collected in Antarctica. And now we have, I guess, close to 100 meteorites from Mars and the same from the moon right now. So not all of the lunar samples were collected by astronauts. Many of them came to the Earth free of charge, and they're curated at Johnson Space Center. And then we had the Stardust mission, which was the first mission to collect samples from a comet nucleus. Actually, this is a sample collected from the coma of the nucleus. The spacecraft flew by comet Vil2 in 2004 and collected thousands of coma dust grains from the comet in this silica aerogel tray shown in the middle upper part of the slide here. And thousands of these little grains made tracks like the ones shown in the lower center, where the particles embed themselves in the aerogel and were then brought back to the ground for examination. And there was also a second tray, back-to-back with a cometary tray, which collected maybe a dozen or 24 interstellar grains that happened to be passing through our solar system at the time the spacecraft scooped them up. And so these are the first collection of fresh interstellar grains that has been made, and probably the only one in our lifetime. One interesting result of this mission was that scientists learned that the early formation of the solar system wasn't exactly as they thought it had been. They knew that grains would spiral in towards the forming sun, but what wasn't appreciated was that many grains spiraled back out again somehow, either spiraled out or were pushed out by the energetic early sun. But many of the grains that end up in this comet were actually formed deep within the inner solar system, closer to the sun. And that was an amazing result from this mission. We also have samples from the sun, the solar wind, collected by the Genesis mission, which launched after Stardust, but came back before it. And it had kind of a hard landing on the ground, as you may know. But the collectors were carefully and painstakingly collected from the desert, clean, and all the science that had been intended for the mission was successfully obtained. And the main result was to understand much better the bulk composition of the sun. And it really wasn't what most scientists thought they would find. We also have samples collected in the lower stratosphere called the cosmic dust collection, which has been going on since 1981. And in addition, we have samples of micrometeorites and spacecraft debris collected in the low Earth orbit by about half a dozen spacecraft and space stations. And those are in the microparticle impact lab. And so on the left is showing one of the WB aircraft that collect particles in the stratosphere. Lower left are some particles collected there, which were a first hint of what cometary grains would look like, because grains coming in from comets and asteroids are all being collected by this program. Of course, we didn't know which were which. In the middle and the bottom is a peek inside the cosmic dust lab. It's the cleanest lab at JSC, obviously, because you're looking at microscopic particles. On the right is the LDUS satellite being retrieved by the shuttle. And then the lower pictures is impacts into portions of that spacecraft. And that's been a really training ground for people who are preparing materials for a space environment. So these microparticle impacts tell us a lot about other things coming in the atmosphere and also about the evolution of the spacecraft debris cloud around the Earth, which humans are making to our detriment. And coming up also are asteroid samples collected from 3 different asteroids, Itokawa, Ryugu, and Bennu. The ones from asteroid Itokawa were collected by a Japanese mission called Hayabusa. And then Hayabusa 2 came next, and those were collected just a couple of years ago by the spacecraft from the asteroid Ryugu. And those are coming back on December 6th, which is less than a month from the day I'm making this recording. That'll be pretty exciting. Then there's a U.S. mission, which costs, again, 5 times as much, of course, because it's a U.S. mission, called OSIRIS-REx, which just collected samples from asteroid Bennu, and those will be returning 3 years from now. So over the past decade, 13 years really, we have asteroid samples coming from 3 different known asteroids, and quite different asteroids as well. And lower right is showing a little cartoon of the laboratories that are being constructed now for these new samples. And I didn't mention it, but there's also a Japanese mission going to Mars that will sample the largest moon of Mars called Phobos. That's called the Mars Moons Exploration Mission. That spacecraft is planned to launch in 4 years from now and return 9 years from now with first samples from the Mars moon's environment. And there's a chance the Martian samples brought back with those, they could have been placed onto Phobos by impacts on Mars. So the first samples from the Mars system return in less than a decade from now. And probably some of those will be at JSC as well, although the bulk will be at the Japanese JAXA Curating facility in Tokyo. So just to recap, this has been a brief introduction to NASA's Asteroid Materials collections. It's not just lunar samples, and it's growing every year. And if you want, you can go to our website, which is shown down below, and subscribe to hear more about these samples. And probably your children and your children's children can be looking at these samples in the future if we're very careful to maintain them as we have before. Thank you very much.